guys, welcome to our chemical engineering tutorial brought to you by the ChemEng student. In this lesson we're going to take a look at some heat transfer interview questions and a complete answer that you should be looking to present when you are in the interview. So we're going to look at 10 of the most common heat transfer related interview questions. So question number 1 is, can you define the main modes of heat transfer? Now I would encourage you to pause the video and attempt to answer each of these questions, and then resume the video and you can compare with our answers here. So we want to define the main modes of heat transfer. So heat transfer is basically done in 3 different ways, namely by conduction, convection and radiation. So those are the 3 key terms that you should include within your answer. Now you would want to expand briefly on what these 3 actually are. So conduction occurs within solids, i.e. the kinetic energy from the particle to the particle. So what that means is the vibration of the solid particles will transfer the heat from one point to the other. Now convection occurs within fluids. This can be both liquids and gases. And this is the movement of the particles themselves within the fluid. And then the radiation occurs through electromagnetic waves, and this is present within all matter and materials. So anything can radiate some form of heat. Now question number 2 will be, what is the driving force for heat transfer? A very common basic question when it comes to heat transfer. Now heat transfer, the main driving force is a temperature difference or a temperature gradient. Now that answer does indeed, cover the question, but we can do a bit more, because ultimately what you want is to answer the question directly, but then provide a little bit more information and some context to highlight that you fully understand the fundamentals of, in this case, heat transfer. So what we can say here is that the greater the temperature difference, the higher the rate of heat transfer and the quantity of heat that is being transferred. And this is evident through the following equation. Now granted there are other variations, but this just highlights the influence that the delta T, so the UA delta T, the delta T is the driving force. So the higher the value of delta T, the higher the value of Q. So even having a piece of paper that you can write this stuff down to illustrate that you understand the process and the principle would definitely set you apart in an interview. The next question will be, explain in what context an LMTD would be used. Now the first thing that you would have to ensure is that you know what LMTD actually stands for, and then apply it to a contextual example. So an LMTD stands for a log mean temperature difference. And the log mean temperature difference is used when there is what we call a non-uniform temperature difference between the streams, say within a heat exchanger. Now if we use the standard arithmetic temperature average, so we take the inlet temperature, the outlet temperature, divide it by 2, then what this assumes is that the temperature difference throughout the entire heat exchanger is the same. Now that in theory would work, but in reality that doesn't necessarily happen, especially when you have parallel or cross current flow. You can get away with a counter current flow, but when it comes to parallel and cross current, you have to use a log mean temperature difference. Now when this is not the case, in that we can use an arithmetic temperature average, we have to account for variations within the temperature difference, because as we know, the driving force for heat transfer is a temperature gradient. So if there is parts of the heat exchanger where the delta T is higher than others, then essentially you're going to have a varying rate of heat transfer. So therefore the log mean temperature difference accounts for the variability of the temperature changes within the entire system. So it just gives you a more accurate delta T value that you can then use in the formulas that you've seen in the previous question. That's a very comprehensive answer to provide serious context to what a log mean temperature difference would be. So using those kind of key terms will definitely set you apart in an interview. And if you want to see this as a pictorial diagram, you can see here that the top one is a co-current system, meaning that the flow is going in the same direction, whereas countercurrent would be the flow is in the opposite directions. Now you can clearly see that the top chart for the temperatures, there's basically no way that the difference between the hot fluid and the cold fluid, the temperatures will be uniform from the beginning, so from point A to point B. So therefore you must use a log mean temperature difference. You can, as I says, get away with it with countercurrent flow. Now question number 4 would be define the distinction between the bubble point and the dew point. And this is particularly prevalent when we are designing distillation columns. So if we start off with the bubble point, then in essence the bubble point is basically the given temperature at which the very first bubble of vapour will be formed, going from a liquid to a gaseous state. Now an example that you could provide is, say you get a pot and you heat it up on, say, your stove or your oven. Then when you see the very first bubble forming in the bottom of the pot, that temperature that you would record is the bubble point. And the dew point must be the opposite. The dew point is the temperature at which the first piece of condensate begins to form, going from a gaseous state to a liquid state. So they're basically the opposite and inverse of each other. Number 5 is state Fourier's Law of Conduction. Now, unless you have been living under a rock, chances are you would have heard of Fourier's Law in the context of heat transfer. That is basically the foundation for heat transfer principles. So if we want the Fourier's Law for conduction, then you basically need to know what the equation is in your head to explain it and then be able to write it down. So Fourier's Law of Conduction basically states that the rate of conduction is proportional to the area that is measured in the normal direction of the heat flow and to the temperature difference within that direction. That's the explanation. Now you would need to ideally present what that equation is, because then what you can do is relate the description to the equation. For example, you have minus Ka multiplied by a differential equation of dt by dx, whereby A is the area, so the surface area of the material, and the dt by dx is the change in the temperature with respect to the direction of the flow, i.e. x is the width or the thickness of the material. Now, in its more general state, it can be expressed as a vector for a multi-dimensional condition, and it's presented by this equation here. Now, the reason you know it is a vector quantity is we have q double prime, but we also have the arrows indicating that we have a mathematical vector. But the first equation is usually the one that we as engineers would use, because we would assume a one-dimensional model. So again, that's another thing you could add in, is that this equation works in 1 dimensions. Question number 6 is, what is the difference between latent and sensible heat? And this is something that I feel that I observe in my students that often trips people up, is the distinction between latent and sensible heat. So latent heat transfer is where the actual temperature of the material does not change. But what does change is the phase of the material. So for example, if we have liquid water and it begins to freeze, then the change from the liquid to the solid is when latent heat transfer occurs. So although it sounds like, there has to be a decrease or an increase in the numerical temperature, latent heat occurs with the heat associated with a phase change. Whereas sensible heat is the change in the temperature of the material, i.e. an increase or a decrease. So usually if you were to put, say, something in a freezer, the cycle would be that you lose sensible heat to 0 degrees Celsius. Then a phase change or latent heat will occur, i.e. we go from the liquid to the solid. Once we have become solid, we then lose further sensible heat. So that's the key distinction between these two types of heat transfer. Now explain the two types of convection. So we've already defined, potentially in the interview they could say, define the modes of heat transfer, which is fine. And when you mention convection, they may alleviate and elaborate on one or more of these in depth, and the key one is usually convection, because there is two types. So they may want you to further expand on your fundamental knowledge of heat transfer. So the first one would be natural convection, and this occurs in a free manner due to simply the fluid motion as a result of the change in densities between the warmer and the colder fluids. And these changes occur due to the temperature difference. So for example, if you think of just general air, when you have heat that is applied, the air rises to the top of the room. But as it cools, it then begins to fall back down. So this motion between rising and falling due to the change in the density is called natural convection. There's no input into the system. Now the other one, the opposite, would be forced convection. And this is where the fluid has been put in motion by a mechanical force, usually in the form of a fan or a pump or an agitator. So it is getting a helping hand. Now a bonus tip here would be you can actually state which one is more efficient at transferring heat. So the more efficient one would have to be forced convection, because we are creating a more turbulent system. And turbulence and heat transfer are directly proportional to each other. But again, we talk a lot about this, all of this stuff, in copious amounts of detail in the other heat transfer videos on our YouTube channel. I'll put a link in the description to some of them, but as well as our incredibly popular heat transfer course, which is fully comprehensive. I'll put a link in the description to that if you are interested in going into the depths and the core of heat transfer. Question number 7 would be, what is the Stefan Boltzmann Law? So just like Fourier's Law, this is a very common correlation or law that is applied within heat transfer, more so at the latter stages of a degree. So you don't necessarily touch on this in the fundamentals, this kind of progresses to the end. But the Stefan Boltzmann Law basically states that the total radiant heat energy that is emitted by a surface is directly proportional to the absolute temperature raised to the power 4. Now this is a experimentally validated correlation, so you don't have to prove it, but you have to know what the relationship actually is, what it relates to. So you have the total radiant heat energy, so that's the EB. Then you have sigma T to the power 4. So that's the absolute temperature, which is in degrees Kelvin, to the power 4. Now, the sigma is the Stefan Boltzmann constant, which is given as 5.6 times 10 to the power minus 8. And this is in watts per meter squared Kelvin to the power 4. So you can actually see that the units of the total radiant heat energy would be watt per meter squared, which makes sense. So simply in the interview explain what the law is, and even if you can recite what the Stefan Boltzmann constant is, that will definitely put you well above the average person for the interview. Question number 8 is explain what a black body is in terms of emissivity. So again, this is building upon the Stefan Boltzmann law. It's more centered towards radiative heat transfer, which always features at the latter stages of the degree program, because it is quite complicated. But a black body, in its simple terms, is a fictitious entity that has the maximum attainable emissive power at any given temperature. So what this basically means is that because all material will radiate heat of some order of magnitude, the black body emissivity is equal to 1. So the emissivity is basically between 0 and 1, 1 being that it has the largest and maximum total emissive power. So basically the ratio to the total emissive power versus the emissivity of the black body itself, they would be equal to each other, so as that this equation would be equal to 1. So therefore what you are saying is a black body emits all of the allowable maximum attainable power for that given temperature that you are operating in. Now it is fictitious because there will be some loss, there will be some resistance, there will be some absorption of the heat itself. It will not radiate 100% of the maximum attainable emissive power. But by explaining and using these key words and even presenting this equation will cement your understanding of black body radiation. Number 9 is, can you explain what NTU is? So this is like the log mean temperature difference, whereby the interviewer may not actually say what the acronym stands for. They are going to assume you know what NTU stands for. Because if you don't know what NTU stands for, there's no way that you could answer the question. So what I would do first is say what NTU stands for. So NTU in the context of heat transfer is it stands for the number of transfer units. And this is used within heat exchanger design and analysis problems. And it's governed by this equation here, whereby it is basically a measure of the effectiveness of the heat exchanger itself in relation to the thermal capacity ratio. So what that's saying is you have, the overall heat transfer coefficient, you have the surface area, you have the basically the amount of capacity energy, the minimum capacity energy needed for this particular system. So you could actually, calculate what ChemEng actually is, and there is a ton of correlations. Again, we look at that in our heat transfer course, where you get all the resources in order for you to calculate ChemEng, and you could have Cmax and so forth. But the number of transfer units will basically state how many units you will need in order to achieve your target requirements. So using those kind of keywords will, cement the idea that you know what you're talking about, and especially by simply defining what NTU stands for. Now, it can also be expressed in terms of thermal resistances as well, because the thermal resistance is basically the inverse of U multiplied by A. And we have videos on thermal resistances. I'll put a link in the description to some of these heat transfer videos that you can have a look at if you're interested in learning some more detail about thermal resistances. Now, the final question, which I thought we would end with probably one of the most fundamental and popular questions, is can you explain what Nusselt number actually is? Now, Nusselt number is, in simple terms, a dimensionless quantity or dimensionless number that is used to describe the convective heat transfer between a fluid and a surface. And you must know these dimensionless numbers. This is one of a few off the top of your head. So you would need to be able to define the equation. Now, there is subtle variations in the equation, but generally speaking, Nu is equal to dH over K. So what you're basically saying here is you have the heat transfer coefficient, the thermal conductivity, and the thickness of the material as well. And that will allow you to determine Nusselt number. And from there, in the context of heat transfer, Nusselt number is described or expressed as functions of Reynolds number and Prandtl number, because the rate of heat transfer, as we mentioned before, is highly dependent upon the flow regime and the fluid type, because every fluid and every solid has different heat transfer properties. So there is a long list of correlations between Nusselt number and Reynolds and Prandtl number. So we have a full description video on Nusselt number. Again, I'll put a link in the description to that, and that goes into real detail on what Nusselt number actually is in the context of heat transfer. So that's the end of this lesson. Thanks for watching. Hopefully this was helpful in giving you a taste of interview questions that would be related to heat transfer. This is one of a series of interview tutorial questions that will be coming in the coming weeks and months. So if you have any recommendations on specific types of interview questions, then please let us know in the comments below. We also have just general technical interview questions, videos on that as well, so you can check them out if you want more general technical interview questions. But thanks for watching. If you liked this video, please like and subscribe to the channel. It really helps us reach as many chemical engineering students as possible. Thank you for your time, and we look forward to seeing you in another video.